So I'm going to kick off with the first talk, and I just want to make the point that the many colleagues is about 55 people who co-authored 2 papers in Nature in the last 6 weeks that I'll mainly be talking about today. So coral bleaching has increased in frequency hugely over the last 40 years. So the Great Barrier Reef has now bleached 4 times. In 1998, 2002, and back-to-back for the first time in the last 2 years. 2 of those events have been strong El Niños, 1998 and 2016. The other 2, the second and the most recent event, have not been during El Niño conditions. So globally, we're seeing an increase in the frequency of these mass bleaching events, and increasingly we're seeing them outside of El Niño conditions, and the projection by the climate models is that we could see annual bleaching in 30 or 40 years with business as usual greenhouse gas emissions. So we have a narrow window of time globally to reduce emissions to avoid a disaster for the world's coral reefs. Bleaching is caused by exposure to heat. So the link between global warming and coral bleaching is incontrovertible. So in our first Nature paper this year, in the March 16th issue, we published this graph. This graph was co-authored by 46 people. So the x-axis here is heat exposure, measured as degree heating weeks, which is a combination of the intensity of the heat in degrees centigrade and the duration of the exposure. And the y-axis is the percent bleaching that we observed underwater, each dot being a replicate location along the Great Barrier Reef. So you can see there's a nonlinear response. There's a threshold at about 2 or 3 degrees of degree heating week exposure, and above that level of heat, you get more and more bleaching, approximating 80 or 90% above 6 or 8 degree heating weeks exposure. That degree heating week data comes from satellites as part of our ongoing collaboration with NOAA in the United States. So the Nature paper, ironically, was published 2 days after I got back into an airplane to record the 2017 bleaching event. So in this paper, we describe the first 3 events, and the top 3 maps show the footprint of the bleaching. So in 2016, the bleaching was very much a northern affair, whereas in 1998 and 2002, the north more or less escaped bleaching. So it's colored green in the top middle and left graph. That pattern, those distinctive footprints of where the bleaching occurred in each of those 3 events, matches very closely the corresponding footprint of where the water was hottest for longest. So the bottom 3 maps are heat maps, no pun intended, of where the temperatures were highest. So blue is cold and red is very hot. So you can see for 2016, the north-south gradient in the bleaching can be explained very clearly by the north-south gradient in heat exposure. Tragically, we've now seen back-to-back bleaching, and our capacity to get this data analyzed, peer-reviewed, and published is actually being overtaken by the frequency of the back-to-back bleaching event. So the next couple of slides I'll show you are in the public domain. There are preliminary results which we have released through press releases or through blogs like The Conversation in order to make the public aware of what's happening to Australia's coral reefs even before we can publish it, because as you know, the publication cycle takes a year or more, and a year is pretty quick. So this is our preliminary map of the extent of bleaching in 2017 and a comparison with 2016. So you've already seen a more complex version of the 2016 map in the last couple of slides, which show that the most extreme bleaching was in the north. So the red dots are reefs that were scored from the air as having more than 60% bleaching. 60% of the colonies were white. The green dots are reefs that have less than 10% bleaching in 2016. So you can see the northern third of the Great Barrier Reef was very severely bleached in 2016. That was a record heat wave. And in 2017, the bleaching moved to the central region, meaning that the combined footprint is fully 2/3 of the length of the Great Barrier Reef, including the Torres Straits, which was impacted in 2016. One of the research questions we're interested in asking with this back-to-back research is whether the intensity of bleaching in 2017 is contingent on the experience of the corals 1 year earlier. And we're still analyzing that data, but I think that is the case. So we saw relatively mild bleaching in the north this year compared to last. I think the reason for that is not necessarily good news. It's because coral cover there is so low now after extensive mortality, which I'll show you in a moment, that the only corals remaining are very tough. So many of the reefs in the north that we scored as mildly bleached this year, we were looking at mildly pale Porites bommies on the upper slope, and they have survived, whereas the more susceptible species like Acropora, Montipora, and soft corals have largely disappeared from the northern 700-kilometer section. I also suspect, and we'll know the answer very soon, that the bleaching we recorded in the central section this year is more extreme than we might have expected given the level of heat exposure this year, because the corals were weakened by their experience last year. Corals in the central region have bleached twice, and we think they're physiologically damaged. Many of them are injured, some of them are diseased, and it's possible that they bleached more readily this year than they would have otherwise for the amount of heat exposure that they've experienced in 2017. So my point is there are lots of interesting research questions like the role of contingency in history that we can ask with this sort of information. We're not just in the business of describing gloom and doom. This research is very definitely question-driven, hypothesis-driven, and that's why it's leading already to a series of high-profile papers in places like Science and Nature. Sorry, wrong way. This is our preliminary map of mortality for 2016, and we published this in collaboration with the Great Barrier Reef Marine Park Authority and the Australian Institute of Marine Science, hence the 3 logos. Again, this data is only now about to be submitted to a journal. We'll be sending this one to Nature as well. So this is our preliminary release to the public to inform everyone of what's going on the Great Barrier Reef. We published it in the conversation. So bleaching doesn't necessarily lead to coral mortality, but when the bleaching is extreme, we can often document very high levels of mortality. So the bad news from 2016 is the red zone. That's the northern coastal strip and mid-shelf strip and some of the southern ribbon reefs north of Cairns. So the area from about Port Douglas all the way up to New Guinea, in red there, the median loss of corals, and this is measured underwater, not from aerial scores, was 67% loss. The range there from 11 to 35%, if you can read it for the north, sorry, from 47 to 83%, is the 2 middle quartiles. So what that means is that the top quartile for the red region lost at least 83% of its corals, typically 85 to 95% of the coral cover was lost in that red region. That is an enormous loss. When mortality is as extreme as that, the concept of winners and losers more or less evaporates. There are very, very few winners when you have 90% plus mortality. So in that red region, and to a lesser extent, the adjoining orange region in the far north, we saw coral taxa bleach and die that normally bleach very little and normally survive a bleaching event, the so-called winners, the heat-tolerant species. during an extreme event like this, we saw 50 and 100-year-old corals bleach severely and subsequently die. And for that reason, I believe the northern red region, the mix of species in that region has changed probably forever, because the time interval between that bleaching event and the next one turned out to be 1 year. We were hoping for a decade, which hasn't eventuated. So the big unknown for the future of coral reefs is really how the frequency of recurrence, the interval between pairs of severe bleaching events, is changing through time. And that's another paper which we now have in review in Science, which shows that globally in the 1980s, the median return time between recurrent severe bleaching events was 25 years, compared to the past decade, when the median return time between pairs of recurrent severe bleaching events is now 5.9 years. And that's nowhere near enough time for a full recovery of coral assemblages. Even the most weedy coral assemblages, dominated by Acropora and Poecilopora, take optimistically a decade for a reasonable recovery to take place. So the summary of all of that is that the footprint of the back-to-back bleaching is about 1,600 kilometres, roughly 2/3 of the Great Barrier Reef. The southern third, luckily, did not bleach either this year or last year. The severity of the bleaching event in 2016 and again in 2017 is far greater than either 98 or 2002, and the mortality is unprecedented. So the average Great Barrier Reef-wide mortality rate in 2016, if you get the average of all of those different colored zones, taking into account the area of reefs in those different zones, was 30%. Gabrumpa reported 22% in June last year, and both they and our centre have updated that event to 30% loss by October, November, 6 months after the peak of bleaching last March. Our estimate of the additional mortality in 2017 is 19%. So, in other words, 49% of the corals in the range of shallow water habitats that we've all surveyed have been lost from the Great Barrier Reef over a period of less than 18 months. And that, by any estimate, is a game changer. The recovery time, as I said, is for those lost corals is likely to be far greater than the return time. The big question now is, when will we see the 5th, 6th, and 7th severe bleaching event occurring on the Great Barrier Reef? So I want to change tack now and talk about a different paper. So mostly here I've been talking about a couple of papers that are in review and our initial paper in the March 16th issue of Nature. What are we going to do about all of this? Moving beyond the gloom and doom, what are the appropriate responses in terms of governance and management of coral reefs to deal with these issues? So you'll hear several talks about that today from Tiffany Morrison, Josh Sinner, and tonight from Michelle Barnes. Those three people are social scientists, so they'll be talking about the human dimension, the governance and management dimension of coral reefs much more knowledgeably than I can. So in the June 1st issue of Nature, we published a new paper. The title is Coral Reefs in the Anthropocene. It's a review or concept paper. It's quite a substantive piece of work. It's 9 pages of Nature, where we look to the future and ask the question, how can we improve on governance of the world's coral reefs? Clearly what we're doing now is failing, and we need to revolutionize our science and also our governance and management of reefs. So we try in that paper to provide a blueprint, a way forward, and in Australia that's incredibly important. Australia has a plan called the Reef Sustainability 2050 Plan. It's now the framework for managing the Great Barrier Reef out to 2050. I'll talk a little bit more about that plan in a moment, but basically the back-to-back bleaching of the Great Barrier Reef means that that plan needs to be radically changed and radically improved, and everyone involved, I think, recognizes that. I've made that point. I want to change tack now and talk not just about climate change, but also about the other drivers, the other interactions between people and the coral reef ecosystems that are changing them as we speak. So this is an example of multiple drivers or proxies of those drivers. And the photographs show human activities like shipping and how they impact the reef. So the top pictures are grounding. Then we've got interactions between ship anchors and seagrass beds. And at the bottom, we've got dredging. And the Great Barrier Reef has been very extensively dredged for mainly for export of fossil fuels from 3 coal ports in the last decade, and there's more dredging planned for some of those ports. So if we look at the bottom graph, that steep curve is for recreational boat licenses, which is a metric of recreational fishing pressure on the Great Barrier Reef. So it's not just climate change that's impacting the world's coral reefs. The 3 big drivers or categories of drivers are pollution, overfishing and fishing-related impacts, and of course, climate change. We tend to deal with each of those one at a time, and our efforts to look at the interactions between multiple drivers, I think, are still very much in their infancy. For example, the 2050 plan is basically a plan for improving water quality on the Great Barrier Reef. It has ambitious targets for reducing sediment loads and nutrient loads entering the Great Barrier Reef as runoff from land. That's terrific. But the Great Barrier Reef plan, all the way out to 2050, does not address climate change, and it does not address a slew of issues around fishing. It does, in the preface, talk about the importance of understanding cumulative impacts and interactions between multiple impacts, but there's nothing in the plan that actually operationalizes cumulative impacts. For instance, there isn't a target for improving sediment load that's contingent on some other driver, which would be one way of dealing with multiple interactive drivers. So in our concept paper called Coral Reefs in the Anthropocene, which has 13 authors, we do look at the beginnings of a framework for dealing with multiple drivers or cumulative impact. So this is a model output. It's a 3-dimensional graph, and the 3 axes are the 3 major drivers that reefs around the world are experiencing. So climate change on one axis, pollution, nutrient load on the other, and fishing on the vertical axis. And the volume of the cube is occupied by reefs that are in different conditions. So in the bottom left, the red section is healthy coral reefs where those 3 drivers are all at a low level. So pollution loads are low, fishing pressure is low, and climate change impacts are also low. The curved interface between healthy reefs, unstable, alternate stable state regions, and degraded reefs in green, those interfaces are curved because of the nonlinear interactions between those multiple drivers and the feedbacks that occur in the system, which I'll explain very briefly in a moment. You can think of that cube as being occupied by 3,000 data points, each one representing an individual reef on the Great Barrier Reef. So many of the reefs are in the red zone. The ones that are most securely in the red zone, towards the bottom left corner, are reefs that are offshore in the southern part of the Great Barrier Reef that have very low levels of nutrients that haven't yet been bleached, and where fishing pressure is very low. In the green region, we've had reefs there for many decades. Coastal reefs in the central region of the Great Barrier Reef, in particular, have been degraded from time before the Great Barrier Reef Marine Park was established. The bleaching event, the back-to-back bleaching that we've just seen, will have seen many hundreds of reefs lurch from the red part of that graph towards the green part. So you can think of it as having a temporal dynamic as well. So this modeling exercise is simply the beginnings of trying to gain an understanding of how multiple drivers interact and how they collectively change the dynamics of the ecosystem. So the curvature in the interface between those three different conditions of reefs are driven by feedbacks. So when you put a reef under pressure, let's say you go from low to medium to high nutrient levels, the response of that ecosystem is almost never a straight line. It's never, very rarely, linear. Typically what happens is there's not much effect of a small increase in a driver, but then there's a critical region where as the driver increases by a small increment, you get a bigger and bigger response by the ecosystem, leading to a nonlinear or sometimes a threshold dynamic. That nonlinearity is caused by feedback. So we can think of three different types of responses by the ecosystem shown by these curves to an environmental driver. So the driver could be climate change, pollution, fishing pressure, or some combination of all three. And the y-axis is the condition of the ecosystem. So there could be a smooth response on the left. If there's feedbacks, you'll start to see a nonlinearity leading to a threshold. And if the feedback is strong enough, then you get a response curve which curves back on itself, leading to what's called hysteresis. So these nonlinear responses are incredibly important for understanding the interactions between multiple drivers. So our current thinking around drivers being additive, synergistic, or antagonistic is outmoded. It's incredibly linear in its thinking, and we need to get to a new understanding of how cumulative impacts, multiple drivers interact that incorporates these feedbacks and these interactions. So in our concept paper in Nature, we offer this as a new framework for future management of coral reefs. So each of these graphs shows multiple drivers on the x-axis going from a weak level of stress on a reef to a high level, and the y-axis is the response of the reef. So the Great Barrier Reef 2050 plan is innovative in that it is attempting to modify a driver. That driver is water quality. So the attempt shown there by the red arrow is target-based to reduce the sediment loads and nutrient loads of the Great Barrier Reef so that the ecosystem is pushed away from a tipping point that would lead to further degradation. So that's one way that we could deal with impacts on reefs. Of course, we very rarely successfully modify drivers. Most of the drivers impacting the Great Barrier Reef, shipping impacts, coastal development, fishing pressure from recreational fishers, are all increasing, and we don't have mechanisms currently in place to reduce those drivers or to cap those drivers. As I said, the 2050 plan is focused on water quality pretty much only. Another way, shown with the middle graph, is to manipulate the threshold. And I haven't seen it stated this way, but that is effectively the concept behind attempts to artificially manipulate the gene pool of corals to make them less susceptible to bleaching, assisted evolution, so-called. But I worry about whether that's actually scalable to anything meaningful outside of a laboratory. And the story I told you earlier about the bleaching scores in the north being less extreme this year compared to last year because of a shift in the mix of the species, that's an example of that kind of dynamic in the middle, where the assemblage, the mix of species now, is tougher compared to the mix of species before. So globally, although it's very poorly documented, we are seeing a decrease in the relative abundance of heat-tolerant species and an increase in the relative abundance of the tougher species that are less susceptible to bleaching and have better survivorship after bleaching events. So that's a different dynamic from the one on the left, but it does offer other management options in terms of toughening up the ecosystem through interventions to move it away from a dangerous threshold. And finally, the other approach is to change the shape of the response curve to get rid of the threshold or to move the threshold further to the right. And an example of that actually comes from the social realm. If you think of the feedback involved in people installing solar panels on their roofs, as the price of electricity goes up, people are incentivized to put the panels in. That means the customer base of people buying electricity from the grid shrinks, so the price goes up further, so they buy panels too. That's a strong feedback, and that feedback could be accelerated through government intervention, for instance, to pay people more for the electricity that they supply into the grid. So these feedbacks can be manipulated and managed, and they can change the dynamic of the system to make it more robust. And that's the third different approach. So to summarize all of that and its implication for the plan, 1 minute. The plan's objective is to improve the condition of the Great Barrier Reef decade on decade so that it once more resembles the condition of 1981 when it was inscribed on the World Heritage Area list. That objective is no longer attainable. And UNESCO itself is struggling with this. So we have been advising UNESCO in the last few months on the impact of coral bleaching, not just on the Great Barrier Reef, but on World Heritage areas globally that have coral reefs in them. There are 26 of them. The plan needs to be more forward-looking because the idea of maintaining the status quo or going back to what the condition of the reef looked like 40 years ago is no longer attainable. And a better option, I think, is to accept the change is happening and to steer that change into the future, a forward-looking approach that maintains a healthy and functioning coral reef, but a different coral reef into the future. That's it. Thank you very much.